Welcome to this coding problem walkthrough. Today, we'll be exploring problem number 97, interleaving string. This problem challenges us to determine if a string can be formed by interleaving two other strings while preserving their character order. Let's dive into the problem and break it down step by step. In this problem, we are tasked with determining whether a string S3 is formed by interleaving two other strings, S1 and S2. The key idea behind interleaving is that all the characters from S1 and S2 appear in S3 in the same relative order as they appear in their respective strings. This means that while the characters can be mixed together, the order of characters within S1 and S2 must be preserved. Additionally, the length of S3 should exactly match the sum of the lengths of S1 and S2. The input consists of three strings, S1, S2, and S3, and the output is a Boolean value, true if S3 is an interleaving of S1 and S2, and false otherwise. Let's break this process down further with examples to understand how interleaving works and what constraints we need to consider. For the first example, we have S1 as ob, S2 as axi, and S3 as axiB. Here, the output is true, as S3 can indeed be formed by interleaving S1 and S2. To see how, we start by taking the first of from S1, followed by another of from S1. After that, we take X from S2. The process continues with the next A and B from S1, then finally Y from S2. Notice that all characters from both S1 and S2 appear in S3 in the correct relative order, and the length of S3 matches the combined lengths of S1 and S2. Now, for the second example, S1 is ABC, S2 is def, and S3 is absef. The output is again true. This is because the interleaving process can be visualized as follows. We take the first character from S1, then D from S2, followed by B and C from S1. After that, we take E and F from S2. This ensures that all characters from S1 and S2 are present in S3 in the correct relative order. Additionally, the length of S3 is consistent with the combined lengths of S1 and S2, fulfilling another requirement for interleaving. In the third example, let's consider S1 as ob, S2 as axi, and S3 as abaxi. Here, the output is false. While S3 does contain all the characters from S1 and S2, their relative order is not preserved. For instance, the second A in S1 comes after the X from S2 and S3. This violates the requirement that the characters from S1 and S2 must appear in S3 in the same relative order as they do in their original strings. Thus, S3 is not a valid interleaving of S1 and S2. Now, let's look at some constraints and edge cases to better understand the problem. First, if either S1 or S2 is empty, then S3 must exactly match the non-empty string. For example, if S1 is an empty string, S2 is ABC, and S3 is also ABC, the output is true. However, if S3 is ACB, the output is false because the order of characters in S3 does not match that of S2. Similarly, if the length of S3 differs from the combined lengths of S1 and S2, the output is automatically false since it's impossible for S3 to be a valid interleaving in that case. Finally, we need to consider cases where characters in S1 and S2 overlap. For example, if both S1 and S2 are AAA and S3 is AAAAA, the output is true because it's possible to interleave the characters while maintaining the correct relative order. However, if S3 is AOB, the output is false because the extra B in S3 cannot be accounted for by S1 or S2. These constraints and edge cases help us ensure that our solution is robust and handles all possible scenarios correctly. To tackle the problem of determining whether S3 is an interleaving of S1 and S2, we can consider a few different approaches. First, the brute force approach involves trying all possible ways to interleave S1 and S2 to form S3. Starting with the first character of S3, we recursively decide whether to take the next character from S1 or S2. If both options are valid, we continue down both paths. At any point where the characters do not match or the lengths don't align, we backtrack. While this method is intuitive, it's incredibly inefficient since it explores all possible interleavings, resulting in exponential time complexity. Next, we have the dynamic programming approach, which optimizes this process by avoiding redundant calculations. Here, we use a 2D DP table, DP, I, J, to determine if the first I characters of S1 and the first J characters of S2 can combine to form the first I plus J characters of S3. Key observations include handling edge cases, like when S1 or S2 is empty, and building the solution iteratively based on matches between characters in S3 and the respective strings. This approach improves efficiency significantly, reducing the time complexity to O(m*n). The dynamic programming approach, while efficient, uses O(m*n) space for the DP table. However, this can be optimized to O(n) using a rolling array, which helps minimize memory usage. Another alternative is the recursive approach with memoization. This combines the simplicity of recursion with the efficiency of caching. Instead of recalculating overlapping subproblems, we store their results in a hash map or a 2D array to avoid redundancy. This method shares the same time complexity as the DP approach, O(m*n), but may use slightly less space in practice. However, it still requires O(m*n) space for memoization storage and the recursion stack. While both the DP and memoized approaches are efficient, the choice between them often depends on the input size and practical considerations like stack depth and memory overhead. Ultimately, the dynamic programming approach was chosen as the most suitable strategy for this problem due to its clarity, efficiency, and deterministic nature. Although the recursive with memoization approach is equally efficient, the DP approach avoids recursion overhead and is more robust for handling larger inputs. The key insight, or the aha moment, was realizing that the problem could be broken down into smaller subproblems by observing that S3 must be formed by combining prefixes of S1 and S2. This naturally led to the DP formulation. There are trade-offs to consider. While DP is slightly harder to implement than recursion, it avoids stack overflow issues that might arise with deep recursion. Additionally, while a space-optimized DP version using O(n) memory is available, starting with the full DP table of O(m*n) simplifies debugging and understanding the problem. This balance between efficiency, clarity, and robustness makes the DP approach the optimal choice for solving this problem in both interview scenarios and real-world applications. To solve this problem, we need to determine if the string S3 can be formed by interleaving two strings, S1 and S2, while preserving the relative order of their characters. Interleaving means characters from S1 and S2 alternate in some way to form S3, but the sequence of characters within S1 and S2 must remain unchanged. First, we consider the combined length of S1 and S2. If it doesn't match the length of S3, then interleaving is not possible. Next, we can think about a recursive approach. Starting with the first character of S3, we check whether it matches the first character of S1 or S2. If it does, we proceed by removing that character from consideration and recursively check the remaining parts of the strings. If we reach the end of S3 and all characters matched correctly, interleaving is confirmed. If at any point no match is found, we return false. This recursive strategy forms the basis of our algorithm, but it can be computationally expensive due to repeated work on overlapping subproblems, which we'll address next. To improve efficiency, we use dynamic programming. Here, we create a 2D table, DP, where DP, I, J, tells us whether the first I characters of S1 and the first J characters of S2 can interleave to form the first I plus J characters of S3. We initialize the table with base cases. For example, DP 0, 0 is true because empty strings can interleave to form an empty string. For the first row and column, we check if S1 or S2 individually matches the corresponding portion of S3. Next, we fill in the table using a recurrence relation. Specifically, DP, I, J is true if either DP, I1, J is true when the current character of S1 matches S3, or DP, I, J1 is true when the current character of S2 matches S3. This ensures we're accounting for all possible ways S1 and S2 could interleave to form S3. By the time we fill the table, the answer will be stored in DP, len, S1, len, S2. This approach avoids redundant computations and ensures we solve the problem efficiently. Dynamic programming is particularly effective here because it helps us handle overlapping subproblems, reducing the time complexity from exponential to polynomial. Furthermore, we can optimize space usage. Instead of maintaining a full 2D table, which takes O, len, S1, asterisk len, S2, space, we notice that each entry in the table only depends on the current row and the previous row. This allows us to use a rolling array, reducing space complexity to O, min, len, S1, len, S2. Additionally, there are some edge cases to consider. If the combined length of S1 and S2 doesn't equal the length of S3, we can immediately return false. Similarly, if either S1 or S2 is empty, the result depends entirely on whether the other string matches S3. These optimizations ensure that our algorithm is not only correct but also efficient in handling both typical and edge case inputs. Let's walk through an example. Suppose S1 is OB, S2 is AXI, and S3 is AXIB. We initialize a DP table with dimensions 4 by 4 because S1 and S2 each have length 3, and we add 1 for the empty string case. The base cases are set first. DP 0, 0 is true because empty strings can interleave to form an empty string. Then we check if S1 matches the initial portion of S3, filling the first column, and similarly for S2 along the first row. From there, we fill the rest of the table using the recurrence relation. For example, DP 1, 1 is true because the first character of S1 matches the second character of S3, and DP 0, 1 is true. After filling all cells, we find that DP 3, 3 is true, which tells us that S3 can indeed be formed by interleaving S1 and S2. The table helps visualize the decision process, showing how each character in S1 and S2 contributes to forming S3. Finally, let's look at key optimizations for the algorithm. One major improvement is using a rolling array to store only the current and previous rows of the DP table, significantly reducing space usage. Additionally, we can terminate early if the lengths of S1 and S2 don't add up to the length of S3, avoiding unnecessary computation. Another optimization is to skip redundant checks for states we've already computed, ensuring that each subproblem is solved only once. These enhancements make the solution not only correct but also scalable, handling larger inputs efficiently. This implementation solves the interleaving string problem using dynamic programming, DP. Here's a detailed explanation of each part of the code. 1. The function isInterleave takes 3 strings S1, S2, and S3 as input. First, it checks if the combined length of S1 and S2 equals the length of S3. If not, it immediately returns false since S3 cannot be an interleaving of S1 and S2. 2. A2D DP table DP is initialized. DP I, J represents whether the first I characters of S1 and the first J characters of S2 can interleave to form the first I plus J characters of S3. The table is initialized with false values. 3. The base case is handled by setting DP 0, 0 equals true, indicating that an empty S1 and S2 can interleave to form an empty S3. 4. The first column is filled by iterating through S1. DP I 0 is true only if DP I1 0 is true, previous state, and the ith character of S1 matches the corresponding character in S3. 5. Similarly, the first row is filled by iterating through S2. DP 0, J is true only if DP 0, J1 is true and the jth character of S2 matches the corresponding character in S3. 6. For the rest of the DP table, the value of DP I, J is determined by 2 possible scenarios. If the ith character of S1 matches the I plus J, th character of S3, then DP I, J depends on DP I1, J. If the jth character of S2 matches the I plus J, th character of S3, then DP I, J depends on DP I, J1. These conditions are combined with a logical OR. 7. Finally, the value of DP len S1 len S2 is returned, which indicates whether the entire S3 can be formed by interleaving S1 and S2 while preserving the order of characters in both strings. This solution has a time complexity of O, m*n, and a space complexity of O, m*n, where m and n are the lengths of S1 and S2, respectively. It efficiently handles the problem within these constraints, ensuring correctness for all edge cases. Here, we start by importing the necessary utilities and defining our solution class. The main function we implement is isInterleave, which checks whether S3 is an interleaving of S1 and S2. First, we perform a quick check. If the combined lengths of S1 and S2 do not match the length of S3, we can immediately return false since it's impossible for them to interleave. Next, we initialize a 2D Boolean array DP where DP I, J will represent whether the first I characters of S1 and the first J characters of S2 can form the first I plus J characters of S3. We set DP 0, 0 to true because an empty S1 and S2 can trivially form an empty S3. Then, we fill out the first row and first column of the DP table. For the first row, we check if each prefix of S1 matches the corresponding characters in S3. Similarly, for the first column, we validate prefixes of S2 against S3. These base cases ensure that we correctly initialize our table for further processing. Now, we move to the nested loops where we fill out the rest of the DP table. For each cell DP, I, J, there are two possibilities to consider. First, if the character from S1 at index I1 matches the character at S3's corresponding position and the previous state DP, I1, J, is true, then DP, I, J, becomes true. Alternatively, if the character from S2 at index J1 matches the corresponding character in S3 and DP, I, J1, is true, we also set DP, I, J, to true. This ensures that we account for all valid ways of interleaving the strings. Finally, the result is stored in DP, S1.length, S2.length, which tells us whether the entirety of S1 and S2 can interleave to form S3. The function then returns this result. To solve the problem of determining whether S3 is formed by interleaving S1 and S2, we start by performing an initial length check. Here, the lengths add up correctly, the sum of S1 and S2 equals the length of S3. This means it's possible to interleave them, so we proceed. Next, we initialize a dynamic programming table. This table has dimensions of len S1 plus 1 x len S2 plus 1 and is initially filled with false. The reason for these dimensions is that we need to account for all prefixes of both S1 and S2. We set the top left cell, DP 0, 0, to true because an empty S1 and S2 can always form an empty S3. Then, we start filling the first row, corresponding to cases where only S2 contributes to S3. For example, the first character of S2, D, matches the first character of S3, so DP 0, 1 is true. However, the next character of S2, E, does not match the next character of S3, so DP 0, 2 remains false. This process continues for the rest of the row. Now, we move to the first column, which corresponds to cases where only S1 contributes to S3. We compare each character of S1 with the corresponding character in S3. For instance, the first character of S1, matches the first character of S3, so DP 1, 0 is true. Similarly, the second character of S1, B, matches the next character of S3, so DP 2, 0 is also true. However, the third character of S1, C, does not match the next character of S3, so DP 3, 0 remains false. After initializing the first row and column, we proceed to fill the rest of the DP table. At each cell, we determine whether the prefixes of S1 and S2 can interleave to form the corresponding prefix of S3. For example, at DP 1, 1, either we extend from DP 0, 1 and match a character from S1, or from DP 1, 0 and match a character from S2. By the end, the final DP table indicates whether the entire S3 can be formed by interleaving S1 and S2. In this case, the bottom right cell, DP 3, 3, is true, confirming that the interleaving is successful. Here, we analyze a case where interleaving does not succeed. The input strings are S1 equals ABC, S2 equals def, and S3 equals abdef. The initial check confirms that the lengths match, so we proceed to initialize the DP table, just as before, and set DP 0, 0 to true. We then fill the first row and column based on the matches between S1, S2, and S3. For instance, the first character of S1, matches the first character of S3, so DP 1, 0 is true. Similarly, the second character of S1, B, matches the next character of S3, so DP 2, 0 is also true. However, as we continue filling the table, we encounter situations where neither character from S1 nor S2 matches the next character in S3, leading to false entries in the DP table. For example, at DP 2, 1, there is no valid way to interleave S1 and S2 to match S3 up to that point, so the cell remains false. By the end, the bottom right cell, DP 3, 3, is false, indicating that S3 cannot be formed by interleaving S1 and S2. Finally, we consider an edge case where all input strings are empty, S1 equals, S2 equals, and S3 equals. The initial length check shows that the lengths match, so we proceed. Here, the DP table is trivially a single cell, DP 0, 0, which we set to true during initialization. This makes sense because an empty S1 and S2 can always form an empty S3. Since there are no characters to compare or additional rows and columns to fill, the final output is determined directly from dp 0. The result is true, confirming that the strings interleave successfully. This example highlights how the DP approach handles edge cases naturally, without requiring special handling. Overall, the key observations are that the DP table tracks whether prefixes of S1 and S2 can interleave to form prefixes of S3, and the conditions for each cell depend on whether we can extend from either S1 or S2. The time complexity of this solution is O(m*n), where m represents the length of S1 and n represents the length of S2. Here's how this complexity arises. First, the DP table is initialized with dimensions m+1 by n+1. This initialization involves creating a 2D list, which takes O(m*n) time to fill with default values. Next, the first row of the table, which has n+1 elements corresponding to S2, is filled in O(n) time. Similarly, the first column, with m+1 elements corresponding to S1, is filled in O(m) time. Finally, the nested loop iterates through each cell of the DP table, performing constant time operations such as comparisons and assignments for each combination of indices I and j. Since this loop covers all m*n cells, the time required for this step is also O(m*n). Together, these steps contribute to the overall time complexity of O(m*n). Now, combining these steps, the initialization of the DP table takes O(m*n), filling the first row and column takes O(m+n), and filling the remaining cells of the table takes O(m*n). Among these, the dominant term is O(m*n), which determines the overall time complexity of the algorithm. Importantly, the time complexity remains the same across best, average, and worst-case scenarios because the algorithm systematically processes the entire DP table in every case. Thus, regardless of the input, the time complexity is always O(m*n). The space complexity of this solution is O(m*n). This is primarily due to the storage required for the DP table, which has dimensions m+1 by n+1 and stores Boolean values for each cell. This accounts for the O(m*n) term. Additionally, the algorithm uses a constant amount of auxiliary space for variables like loop counters and indices, which is O(1). When you combine these, the dominant term is the DP table storage, making the overall space complexity O(m*n). It's worth noting that the space complexity can be optimized to O(n) by using a 1D DP array and updating it iteratively row by row. However, this optimization is not part of the current implementation, which focuses on clarity and simplicity in demonstrating the dynamic programming approach. When comparing the provided dynamic programming solution to a brute force approach, the differences are significant. The brute force method involves recursively checking all possible interleavings of S1 and S2 to determine if they match S3. This results in an exponential time complexity of O(2)m+n, as each step involves two choices, picking a character from S1 or S2. In contrast, the DP solution has a time complexity of O(m*n), making it exponentially faster and much more practical for larger inputs. In terms of space complexity, the brute force approach requires O(m+n) due to the recursion depth, while the DP solution uses O(m*n) to store the table. Although the DP approach uses more memory, it avoids the exponential growth of the call stack, making it a more efficient and scalable solution. The O(m*n) complexity of the algorithm is due to its systematic approach, where all possible prefixes of S1 and S2 up to their respective lengths are evaluated. Each prefix combination is considered exactly once, and this process is bounded by the size of the DP table, which has m*n cells. This ensures that the algorithm is both comprehensive and efficient. In conclusion, the provided solution is significantly more efficient than brute force, with both time and space complexities of O(m*n). While space optimization to O(n) is possible, the current implementation is straightforward and ideal for understanding and teaching the dynamic programming strategy used to solve this problem. One common mistake is confusing interleaving with a subsequence problem. Interleaving mandates that all characters from both strings are used while preserving their respective order. For example, if S1 is ABC, S2 is def, and S3 is absef, interleaving ensures that the relative order of characters in both S1 and S2 is maintained. This is different from a subsequence problem, where characters can be skipped. Another mistake is failing to explore all possible interleaving paths. A greedy approach might prematurely commit to matching characters from one string without considering alternatives, which could exclude valid interleaving sequences. For instance, with S1 as ob, S2 as axi, and S3 as axib, multiple paths must be considered to validate the interleaving. Lastly, edge cases are often ignored, such as when one or more strings are empty or when the lengths of the strings do not match. If the combined length of S1 and S2 doesn't equal the length of S3, it's impossible for S3 to be a valid interleaving, so the function should return false immediately to save computation time. Inefficient recursive implementations are another pitfall. Without memoization, solving the problem recursively can lead to exponential time complexity because the algorithm repeatedly processes overlapping subproblems. For example, it might redundantly compute prefixes of S1, S2, and S3 multiple times, wasting resources. Another issue arises in character comparisons. Some algorithms assume that each character in S3 can only correspond to either S1 or S2. However, when both strings have the same character at their current indices, both options must be considered to ensure all valid interleaving paths are explored. Failing to check both possibilities can miss valid solutions, especially in cases where characters overlap between S1 and S2. During interviews, it's crucial to first clarify the problem scope. Most interviewers focus on validating whether S3 is an interleaving of S1 and S2, rather than generating all possible interleavings. To approach this efficiently, dynamic programming is the preferred method. A DP table with dimensions based on the lengths of S1 and S2 can be used to track interleaving validity. This avoids redundant calculations and ensures a time complexity of O(n*(m). Key observations include the fact that for any prefix of S3, characters must be taken in order from either S1 or S2, which leads to the recurrence relation, dp, I, j, is true if the prefix of S3 up to index I plus j can be formed by interleaving prefixes of S1 up to I and S2 up to j. This recurrence allows the algorithm to systematically validate interleaving while maintaining efficiency. Understanding related problems can deepen your grasp of the interleaving string challenge. For example, LeetCode 115, Distinct Subsequences, shares similarities in handling subsequences but focuses on counting distinct ways to form one string from another. LeetCode 72, Edit Distance, applies a similar table-based DP approach to track transformations between two strings. Of course, LeetCode 97, Interleaving String, is the problem we're currently examining, where validating interleaving is the primary goal. Additionally, LeetCode 10, Regular Expression Matching, involves comparable dynamic programming techniques for string matching, reinforcing patterns that can help solve interleaving-related problems. There are also alternative approaches worth considering. Recursive backtracking is straightforward to implement and excellent for understanding the problem, but its exponential time complexity makes it impractical for large inputs. Dynamic programming with memoization improves efficiency by avoiding redundant calculations, though it can increase space usage compared to iterative methods. Iterative DP is often the best choice for interviews, offering a balance of clarity, efficiency, and lower space usage. However, it may require more effort to implement compared to recursion. Lastly, a breadth-first search approach can systematically explore interleaving paths using a queue, though it tends to be less intuitive and requires additional data structures, making it less common in practice. That wraps up our discussion of the interleaving string problem. We covered the dynamic programming approach for solving it efficiently, along with its complexities and key insights. Thanks for watching, and don't forget to subscribe for more problem walkthroughs. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!